Okay, so welcome friends. I want to talk more about this highly complex network which was generated by one of my network rewrite systems. So I discussed this in a previous video, but as you can see, there's really quite a lot of detail which sort of is crying out to be kind of explored, in my opinion. So the wonderful thing about this structure, one of the great things, is that it was generated just by starting from a cube and evolving some extremely simple rules. And one of the most remarkable things about it is how complex it appears to be. So if we just zoom out, we start to get some kind of an idea of how complicated it is. I mean, if this is all you could see, you would already be thinking, yes, quite complicated. But we can zoom a long way out and it's just rather immense. And as far as I can see, this system just keeps getting more and more complex. So, as I said last time, there's really two different things that we can study about this system. One is about the complexity, whether it keeps increasing in complexity or not. Another is about what kind of large-scale organizational properties are being created. So today I want to do a little bit towards trying to answer that second question. So I want to look at a couple of experiments and we're going to see if we can learn some things about the kind of large-scale structure of these systems. So we can firstly do a few things by eye, but let's look at a smaller network than this because it's rather bewildering. Here's a 3D print of a network that you get after you evolve this system for 200 time steps. And I made it out of elastic material. So it's quite good because you can bend it and stretch it around. And that really emphasizes the fact that the links are just sort of representing topological closeness, and geometric deformations don't make any difference to the real network structure. This system was generated just by starting with the cube and then by applying these 4 different rewrite systems here whenever possible. So at each time step, we look at the surroundings of the black vertex and we decide which of these 4 things should be applied. And by doing this repeatedly, the great pattern that you just saw is grown. So just to demonstrate how this works, let me show you a movie of this network growing. So this is the network evolution starting from a cube. And we can see immediately it starts to tangle itself up. And now watch carefully as this black vertex moves around. It seems to visit these kind of cluster points and organize them in similar ways. So if we just pause the system now, perhaps you can see that there's some similarity in this structure at the top right and a structure at the bottom left. They seem to be getting kind of passed over and end up looking similar. There's also some similarity between, so there's a kind of bobble on the bottom right, and there's some similarity between the two structures near to that bobble, to its upper left and to its upper right. So we're seeing these similar substructures, and it's interesting to notice that when the writer revisits these, they also end up sort of updating in similar ways. So it does seem like there's these kind of pockets which develop, which sort of feed the writer in and transform in similar ways. So there's some kind of fractal aspect going on here. It's difficult to really put a finger on, though. I think it's just that the trajectory at which the writer enters a particular sort of one of these clusters really affects how it's going to actually change it. See, sometimes the writer stays a very long time, like here, and really complicates a particular structure. Like, that was quite unexpected. I didn't imagine the writer would complicate that structure as much as it did. And sometimes these kind of things happen. I mean, this is what you get with chaotic dynamics. But the fact that lots of these similar kind of substructures are appearing means that A, we can probably understand these systems in a lot simpler with a lot simpler visualizations, because it seems like only a few motifs are getting used on the extreme. We're rerunning the system now. And secondly, it seems like um, we're going to get some really large structures, which I'd imagine, if you keep running them, are going to generate kind of copies of the original system, generating within particular seeds. So this is sort of like the essence of self-similarity. What about the way that the writer actually moves? Can we think of anything there? Well, it's coming back from where it came from now. Now it's going back up to the top. Is it going to go in a somewhat circular pattern? Does it go round to the left and then back down and back to the right? No, it's going along a different track now. And now it's going back up again. Yes, it seems just extremely hard to predict how the writer is actually going to move. And if you look at the sort of plot of the writer index over time, then this message is sort of hammered home. The writer moves chaotically, and so it seems quite unpredictable what it's going to do to particular structures. But we do seem to have this tendency for certain motifs to appear in abundance. Okay, so what we wanted to do is some structural comparisons. And so we ask, if we take two vertices which are quite far away from each other, like this green dot here and this red dot, which happen to have a distance of 29 between them, which obviously means this isn't a small world network. Well, if we just look at the kind of networks which are induced upon the nodes close to those balls, then do those networks have similar properties, or are they different? I mean, if they're similar, then that suggests that maybe there's some kind of homogeneity underneath all this apparent chaos. If they're different, then it suggests that this is a kind of differentiating system, perhaps, that is growing different pieces of different styles. So what we'll do then, we'll have a look at the balls around these two vertices of radius 12. Okay, so we'll look at all the vertices within 12 of the green dot and all the vertices within 12 of the red dot. And that gives us these two subgraphs, which I show below. So for the red dot, we get this subgraph on the vertices within 12 of it. And for the blue dot, which is 149 vertices, and for the green dot, we have this subgraph induced on the vertices within 12 hops of the green dot. This is 118 vertices. So what we really want to do then is to compare the structural properties of these two graphs. Because if these are similar, it kind of suggests we might be getting some kind of homogeneity around distantly separated vertices. How do we compare them? Well, one of the first things network scientists look at is the degree distributions. How many vertices have how many links? You make a plot of that, and then you can compare the plot for different graphs and see how different they are. But in these systems, every vertex has 3 links. So rather than looking at the sort of one ball around a vertex, which is the vertices within a distance 1 of it, we'll look at the two balls around the vertices, the vertices within a distance 2 of them, and we'll count how big those different two balls are around different vertices. So this is what we've done, and we've plotted the results here. So the blue points represent the data which came from the structure around the red vertex, and the purple points are for the structure around the green vertex. Those two structures I showed you. And to make these plots, what we did is we looked at each vertex and we determined the sizes of the two balls, as in the number of vertices within 2 hops of each of those vertices, and tallied them up. And we found, for example, in this case here, this purple point on the 8, we found that the number of vertices which have 8 nodes within distance 2 within that structure, the smaller structure I showed you, which was the structure induced around the green dot, well, we found about 54 of the vertices in that structure had this property that there were 8 vertices within the two ball. So this is very similar to a degree distribution. We list the different possible sizes of two balls, and we list how many vertices we found, for which the two balls around them had these sizes. And we see that there are certain peaks and troughs in each of these distributions, and more tellingly, it seems like they're the same in each case. So this suggests to me that there are certain kind of motifs which are regularly occurring, certain kinds of things which are a lot more popular, and the fact that we have troughs as well makes me think it's a rather constrained kind of thing, where these networks are not really sampling from that many different motifs. And so we have some motifs that are very popular and some which are not. And more tellingly, it seems that both the red dots and the purple dots fill a very similar kind of distribution, which to me suggests that even these two quite separated vertices, if we look at the structures on the graphs within 12 of them, they seem to have quite similar structures. And if we just look by eye again at these two systems, they do kind of look quite similar in some ways. I won't go into the details, but I think you can see that both of these networks have quite a lot of similarity. Okay, so here's the network structure on time step 5000, and we can do similar tests to before to satisfy ourselves that nodes in different places tend to grow relatively similar surroundings about themselves. And this also allows us to define a kind of uniform measure of the structure as the graph dimension. So the idea of the dimension of a graph is really a sort of generalization of dimensions of Euclidean space. In two-dimensional Euclidean space, the number of points within distance r of a given point grows like r squared, because the area of a circle is pi r squared. In three-dimensional space, the number of points within a distance r of a given point grows like r cubed, because the volume of a sphere is given by 4/3 pi r cubed. And in general, in d-dimensional space, the number of points within r of a given point is going to be proportional to r to the power of d. And so Basically, the way that we can approximate the dimension of a graph is to look at a particular point and then count how many vertices there are within a distance r of that point and see if that grows in this kind of form. And if it does, then it suggests that for some d. And if it does, then it suggests that d is the dimension of that graph. Now, this doesn't always happen, and there's some tests to see if it works. But in our case, it turns out that this graph does indeed have a robust dimension, and we can work out what it is. It turns out that this structure doesn't have curvature, and if we just count the number of nodes within a distance r of a given point, then we can try and determine what the dimension is d using some algebra, and this is what we find. We find that the number of nodes within the given r ball, as we increase r, increases in such a way as to suggest that the dimension of this system is about 2.2 when we have a large radius. So it looks as if this particular network is growing something like 2.2 dimensional space. So it's interesting that that's not a whole value. That sort of suggests that we have a kind of fractal aspect to this, and it makes something which is between 2 and 3 dimensional space. But the fact that this converges to a definite value is quite encouraging, because it sort of suggests that what we have here is something which is quite a robust measure of space, and we can make similar estimates of dimension around different vertices and we get similar answers. Okay then, so we've had a look at dimension and we've investigated the similarities between vertices which are far away, and we've found that in general the structures around distant vertices tend to be quite similar. So despite the amount of chaos in here, there does seem to be some kind of homogeneity in the sort of large scale structure. And that's what you'd expect if you have a lot of kind of pseudo randomness.